Welcome, this is lecture number 52. In this lecture, we are going to talk about large signal controller tuning in fixed frequency and variable frequency control. That means, in this lecture, we are going to talk about how the tuning method that we have learned, large signal based tuning method that we have learned in the previous two lectures, how it can be implemented across various modulator. That means, we can use fixed frequency modulator, that I have already demonstrated. Then we can also implement in variable frequency modulator. So, different modulator that we can discuss. So, that means fixed frequency current mode control, then variable frequency control method. Then I will also talk about large signal tuning for DC-DC converter or switch mode power converter while driving constant power load, because the constant power load is very now kind of very important topic, because we are talking about data center application, we are talking about electric vehicle application, microgrid application, and such large signal tuning for cascade DC-DC converter in microgrid application. So, these are the things that we are going to discuss today. So, first this part we have discussed, that means if we want to realize our controller tuning, this sigma x, which is nothing but the switching surface and which takes the error voltage into proportional gain plus the current error. Okay. Now, we have seen that this sigma is nothing but the dotted line, right, but actual reality when we want to implement, we never use this ideal sigma here. Why? Because we cannot expect the switch will turn off, and this sigma, it is not like that. So, if we want to just try to keep the trajectory very close to that sigma, then or in this case it cannot be, because it will actually move away. So, we cannot use this sigma, because this is particularly important when you come to steady state. That means, I am trying to highlight this particular part. So, if you take the sigma here, okay, this is a line, this is let us say sigma equal to 0, and suppose this is my trajectory. That means, I want to operate like this, or I want to, because this is under steady state. So, I can remove this. So, I will choose one operating point here. That means, let us say this is my operating point and this is my operating point. This is my load current, this is my reference voltage. Now, I want to operate. So, there is one possibility, that means the trajectory can operate very fast, that means very fast. That means, it turn on and off like inductor current can be negligibly small, very small, and this can lead to some hundreds of megahertz switching frequency, and your device can get burned, because it can damage, because this is kind of a chattering behavior and you may not get any fixed switching frequency, because arbitrary switching. So, we cannot realize an ideal switching surface, okay, under steady state. So, we need to introduce some kind of ripple, we need to allow some kind of ripple, right. So, our basic objective is that we want to allow, that means, we have identified that if I draw the inductor current waveform, the timing diagram, I am talking about the scenario during this part. So, there is one possibility, we can have inductor current like this. There are other possibilities, that means, if I keep this average value constant, this is my I 0, we can also operate like a extremely fast switching. But this may not be desirable, because very high switching frequency may lead to lot of switching loss, and if your device does not support such high switching frequency, it can damage the device. So, we need to select the properly the switching frequency. Similarly, the red one may not be desirable, because the ripple may be too large. So, you may need even some other like So, you may need something like ripple. So, I should be flexible. So, who decide this ripple? whether large, small, whatever. So, this comes from the design point of view. That means, what is my acceptable ripple? Then what is like, because it will help. So, what are the parameters in steady state? Ripple parameter is 1. Then EMI filter, because if we do not specify what is my operating frequency, the switching frequency, then it will be very hard to design EMI filter, because EMI filter should not be designed for a wide switching frequency range, because it will like a low pass filter. So, then you need to put the bandwidth to be very low, and that can affect the transient response of the converter. So, we need to provide some kind of band of switching frequency, some narrow band. I do not want to vary beyond that. Even if you go to automotive product, generally most of the switching converter operate close to 2 megahertz switching frequency, and that is a standard norm from EMI point of view. So, the objective is that we have some ripple constant, that means we cannot reduce too low, then the switching frequency will be very high, and that switching frequency can lead to lot of switching loss and the efficiency can drop. We cannot have very large current ripple. So, who will decide? That means some delta IL which will be desired, that I need to set the desired current ripple. Okay? But how can we incorporate such desired current ripple here? That means I want to implement this switching surface. So, we cannot implement a perfect switching surface for this operation. So, one way we can use the top surface, that means if we add some delta, the green one as my, let us say it is my peak current, something like that, and then this is my peak current, and this the bottom side of the ripple current will be decided by my pulse width modulator time period. That means this I mean we are using one state dependent switching plus time dependent switching. So, it is a combination of state dependent and time dependent, and the pulse width modulator put a time constraint, that means your sum of on and off time should be constant. But the state dependent switching, if we use a trailing edge modulation, then the on time comes from this logic, okay, and the time dependent comes from the timing, like what is the time period. So, the bottom line is this green color can be used as this peak current, and then in pulse width modulator we are actually not using this surface. That means because it is a trailing edge modulation, it just operates based on this one. So, how can we ensure that it will track in average sense? So, then you have to either decide that I will provide some ripple that will follow target trajectory. So, it is a trajectory shaping problem. So, one of the objective, that means we can, and that is exactly we did in the previous lecture. When we derive the optimal parameter, we have ignored the effect due to the ripple, and that is why we are getting slight mismatch, but that is okay. But there we are using a fixed frequency modulator, so there is a constraint, that means you may not get perfect time optimal because of this. But if we use a combination of state dependent and time dependent, this combination, then the time dependent you have three options. One is PWM, where the time period is constant, the total time period is constant. One we know constant off time, where the off time is constant, and the other is constant on time. So, there are three choices. If I do time dependent, one I take total time is constant, that is my PWM, then you can use either trailing edge or leading edge. Constant off time, where the off time is constant, or the constant on time. So, these three can be set to decide what will be my ripple, but in either of these, each of these technique, it only uses one surface and the other surface is open, That means that is driven by the timing parameter. But if you take a hysteresis control, and that we have discussed that this band is represented by hysteresis. So, hysteresis control, it gives a direct, because it is nothing but the state dependent in both sides. So, it is state dependent only, there is no time dependent. That means this require both sigma 1 and sigma 2, that means top and bottom surface, where the average will be your actual sigma. Okay. So, in this lecture we are going to talk about the tuning parameter that we have derived, that equation will remain same, but you can change the modulator, that is it. Okay. That means the whatever we have derived, that will remain same. So, you can apply that large signal tuning both for fixed frequency modulation, then constant off time, constant on time, as well as the hysteresis control. So, all type of across the modulation technique as well as the variable frequency control technique that we have learned in the previous lectures are equally applicable. I mean the large signal tuning, all these different fixed frequency and variable frequency implementation we have learned in the very beginning, like first or second week, that we can bring back and you can apply this large signal tuning for any of this control strategy. So, the first we will talk about peak current mode control. We are using a load current feed forward and this normalization factor will be 1 for buck converter and the feedback gain. So, you can incorporate, once you want to use a feedback gain, then accordingly you have to scale this parameter, because we are using a feedback gain. So, in current mode control, we are for buck converter, the normalization factor is 1, that means we are directly taking load current. But if we use any feedback gain for the current loop, the same gain, that means this is also Kn. If you let us say Kn equal to 0.5, then this Kn should be 0.5. That means the load current and the inductor current, they should be in the same scale. Now, this question may come, this realization require again sensing a load current. But suppose you are talking about you are driving an LED using a buck converter, right? Or you are driving a, let us say constant power load, or you are driving for example, in microgrid application we talk about droop control, right, where we sense load current because we want to adjust the droop. So, there is also available. Similarly, if we talk about LED driving, LED available, right, or battery charging does not require fast transient. So, that does not come into picture. Even for processor application, this load current can be estimated, because if you can understand that the task requirement, if you can interact with the power converter, power management unit with the actual processor load, task scheduler, right, and in digital control that may be possible. So, you can know a priori that the load transient is going to come and the step size of the load can come based on the task intensity, like how much energy is required, right. But otherwise you can estimate this load. So, you can estimate this load current, and we have already shown that even you can apply this tuning for voltage mode where you do not need to sense inductor current or load current, right. So, that is also possible. So, that means you can apply, and this is already reported. Then you can apply this technique for current mode control that we have just now applied. So, current mode control, where the tuning parameters we have already discussed, right, earlier. That means, if you take a PI controller for the current loop, the proportional gain is nothing but it is a function of your L, C, that means the inductor capacitor, the step size of the load, square root of input voltage Vq, where it is equal to Vref for step up and Vin minus Vref for step down. Okay? And we have already discussed that Ki equal to, it is, we have derived this integral gain from small signal model, and Kn is a normalized frequency. So, now we can also apply constant off time, because this is analogous to peak current mode control and constant off time. In fact, we will discuss in the last week or the next week when we take the case study and show MATLAB simulation. So, if we apply peak current mode control, if we apply constant off time control, and then if we apply constant on time control using the same controller gain, how is it going to respond? What are the change difference in the response, right? So, in this case we are again considering PI control h equal to 1, kn equal to 1, but we need to set the right off time so that our time period is maintained at the desired value or at least close to the desired value. We can also apply to constant on time. So, it is only we are changing the modulator. In fact, I have discussed this is not so simple, the constant on time, because here it is just for sake of simplicity we have just taken the constant on time modulator, but it should also include the minimum of time, that also should be included. Here just to show the logic I have shown, but this should be included, and that we have discussed in detail in I think week 2, okay, otherwise it will collapse. And we have also discussed in I think week 4 youth implementation that we should include that minimum on time for constant off time control and minimum off time for constant on time control, otherwise it will collapse during the transient. So, similarly, if we take this one, we should incorporate here, we should incorporate should consider minimum on time, okay, should consider minimum on time. Here also the same tuning parameter that we have derived can be used, and again I am telling we will go in the next week and show one by show all the case study in MATLAB. Now, if we implement hysteresis control, that also you can do. In fact, this will be the perfect solution, because we have talked about if we take the phase plane, our actual switching surface was this, and then we have created this band sigma 1, sigma 2, and we have introduced something like a delta IH hysteresis band, and then that band we can divide and we can implement. So, it is a hysteresis control that we have already discussed, and the same controller parameter, that means this optimal tuning will work for fixed frequency control, hysteresis control, constant on time, constant off time, and we are going to show result in the next week. Now, if you take a boost converter, again you can do current mode control with normalized load current feed forward, and here the normalization factor will be Vref by Vin. And we have derived for step up transient the proportional gain can be approximated by this, for step down it can be approximated like this. Now, we can implement in fixed frequency control, we have to set the right parameter, okay, it is a PI controller, kn equal to this, that means sorry, this is the kn. So, our kn equal to this, then feedback gain, if I take directly the output voltage, or if we incorporate the feedback gain, then how are you going to change the gain, that you have to scale, because since your output voltage is scaled, that means you can think of, if we go back to our sigma, what was our sigma? Our Kp Vref minus V0 plus our normalized current minus the load current. Now, if we use a step down ratio here V0, that means let us say we are talking about V feedback, this is my V feedback, which is nothing but H times of V0, right. So, we cannot use, suppose if we are sensing the feedback voltage, so then our actual, so this is like actual realization will be Kp Vref dash minus V feedback plus In minus IL, and this can be written as Kp. What is Vref dash? Vref dash is nothing but H into Vref. That means, whatever factor you will multiply with the output voltage, that means whatever step down ratio you consider here, the same step down ratio you should consider here, because you need to scale Vref, so that our ultimate objective to reach V0 to be nearly equal to Vref. That is my final objective, right. So, if I do that, that means I can take the feedback gain out Vref minus V0. Now, it is V0. So, this you can think of our Kp dash. That means our Kp dash, that means this is our proportional control, but this is not the optimal gain. So, that means whatever we have formulated, it was Kp dash that we have formulated, that is the optimal gain. So, our actual Kp will be Kp dash divided by H, right, because Kp into H is your Kp dash. So, it is just a scaling factor. Now, for constant of time, again we should, along with this we should use minimum on time and the same PI controller, same normalization factor that we have discussed, that we can use. We can also implement constant on time. Again we need to incorporate minimum of time, and here also the normalization factor is this and same PI controller. So, we will show you that if we use this optimal gain for different modulator, we want to check what is the difference in the performance, and that we will consider. And we can also do hysteresis. In fact, we discussed that hysteresis is a more perfect solution, but remember in voltage mode, we should not use voltage hysteresis control for boost converter because of the non-minimum phase behavior, because because of the non-minimum phase behavior under step up load transient response, the system can collapse unless you put a limit on the time, on time. Okay. So, the voltage hysteresis control, by adjusting the hysteresis band, we can control the switching frequency. For the previous one, we can control the switching frequency by adjusting this on time. We can control the switching frequency by adjusting this off time, and for fixed frequency control, it is already fixed frequency, time period is fixed. So, that means we can implement all this logic. Next, we are coming about the constant power load, because the constant power load we can see many application of constant power load. So, I am taking a buck converter, but this can be also extended for boost converter driving constant power load. Now, if you take data center and telecom application, so two stage converters are quite common, where the first stage, as if the second stage is very tightly regulated, it is considered to be constant power load. So, the first stage like driving a constant power load. The first stage is not very tightly regulated, or it is not very high frequency. The second stage is much faster. So, it is treated as a constant power load. Similarly, if you go to electric vehicle, so the DC-DC converter which is used for drivetrain, suppose your DC-DC converter which is connected between battery and it is output is connected to, let us say, your BLDC motor drive or the permanent magnet synchronous motor drive, where the driver is driving an actual inverter load, right. Now, when the car runs under constant speed, right, then it is a constant power load. That means, it is delivering the constant power where the vehicle is running almost like a constant velocity, right. So, under this condition, then the DC-DC converter which is actually driving the driver of the motor, or basically the inverter, that inverter as well as the motor, the whole thing will look like a constant power load to the DC-DC converter. And this is also another application where, and it is well known, this constant power load actually introduce an incremental negative resistance effect. That means, if it can be approximated like a actual buck converter. So, and we have discussed in week 3, there was one dedicated session where we talk about cascaded converter, where I have shown you using simulation that you can actually, suppose this is your buck converter, inductor, and this is your capacitor, and this can be approximated as minus R, the incremental resistance load. And we have shown that if we use actual two stage converter, and if you simplify the second stage as a constant power load, there will be slight deviation, but the average response are close. So, the constant power load will introduce a negative incremental resistance effect, and it will lead to open loop unstable system. So, if you run this DC-DC converter under open loop. In general, the open loop converter will be unstable focus. So, it will oscillation will keep on growing up, and if we apply a diode like a conventional buck converter, then it will get stuck because of the DC the zero current, and then it may lead to limit cycle oscillation. So, there are extensive research on that, but I am not going to that. So, in this constant power load also our tuning method can be applied for both stabilizing the converter as well as to get the fastest response. And the microgrid also we can have interconnected series parallel converter, where one of the converter can be treated as a constant power load and the other as if it is driving a CPL. So, in large signal CPL, again this buck converter where the load is incorporated here and we are sensing the load current, that means we are sensing this load current. So, here the CPL is also there, it is CPL load is there. So, here the same method, we can take the normalized load current feed forward. So, in buck converter, since the average inductor current same as the average load current, so this Kn will be 1. Okay. So, we can apply and we can set the tuning rule here, and we want to see what will be my tuning parameter when you are driving a constant power load. So, if we set it Kp equal to 2C, because only thing here we are changing, earlier this quantity earlier it was for constant current load we got Kp was equal to approximately equal to 2C by L delta I0 into that your V in Vq, and Vq also we know. Now, here we have replaced delta I0 equal to our power constant power. Yeah, if there is a step change in the power divided by our actual voltage, that is a reference voltage. So, voltage into current is the power. So, the voltage is considered to be nearly constant. So, any step change in power as if can be translated as a load, and that can be replaced and you will get the same result, and this we have published, and this will lead to the optimal response for the buck converter driving CPL. Okay. So, now that means the overall tuning parameter if you want to drive constant power load, and again we will consider this case study in the next week using MATLAB simulation. That means, if you drive a constant power load by setting this optimal parameter, you can get the optimal recovery. It will not only stabilize, but it will achieve fastest transient response. So, here the normalization factor is 1 and your integral gain, it is coming from it is the same as the buck converter driving a constant current load is like it is coming from small signal model, and this can be derived where this is the load power step. Now, the constant power load was in one case can be approximated like another converter, but it need not to be always two converter. This is one of the example. For example, I told you, suppose a buck converter driving or a boost converter is driving an inverter load which is driving a motor, right. So, the boost converter as if is driving the CPL, where the CPL can be treated as a constant power load. But this is another application where the two converters are used, and this is commonly used in data center and telecom application, where suppose if we are using a very high voltage like earlier like a 48 volt. So, here roughly it is nominal 48 volt, and this bus voltage is generally set to 8 to 12 volt, and the output is generally close to 1 volt. So, that means it is a two stage converter, 48 to 12 or 8, then 8 to 1. But now, though there is like extensive research going on regarding direct conversion from 48 to 1 volt, but it is found that even if you use merging two converter, either you can use hybrid switch capacitor converter or isolated converter, or merging these two converter, it turns out to be the effective solution if you use a two stage architecture. That means, in the first stage generally people use a hybrid switch cap architecture to step it down, and in some time LLC converters are used which are very efficient, where you need to maintain very tight voltage regulation like 48 to 12 volt. If you specify 48 to 12, then it can give very high efficiency, and then the second stage you can use a multi-phase converter. So, whatever it is, the two-stage converter, since the second stage are very tightly regulated and it is a very high bandwidth, so this will look like a constant power load for the IBC. And even if you consider two converters separately, so then we can also apply our tuning rule. And this is also used for electric vehicle for auxiliary power supply, because if you are going for 12 volt battery, again you are generating very low voltage, either you can go two stage, or if you are using high voltage, because in electric vehicle we have a high voltage battery, we have a low voltage battery. So, sometime we need to convert from high voltage to low voltage, and then from low voltage battery is driving an auxiliary load. So, all this scenario you can come across two stage converter also. And DC microgrid, you can find multiple converter connected in series parallel. So, it can constitute something like a two stage architecture. So, in such application we can apply our tuning rule, where the two converters are driven separately by two current mode control. This is his own current mode control and this is his another current mode control. Again, each of them is like a buck converter, where we can take any modulator that we have discussed. Either you can apply fixed frequency control, either you can apply hysteresis control, either you can apply constant on time, constant off time, whatever control that can be applied. So, that is why it is a modulator. And here each converter that we are going to see what type of controller structure we are taking. So, it is a current mode control. So, it is sensing the inductor current from here, and we are also sensing the inductor current from here. So, both are current mode control, and in this case we are using a load current feed forward directly, that we have discussed, but for the first stage we do not need to sense the load current here, because we can extract the load indirectly from this expression because we already know we are sensing the bus voltage and we are already regulating the output voltage. From these two voltage information and the output current information, we can directly obtain what is the load current. So, this we have already implemented and we have shown the individual converter we can. So, for the first stage IBC, it is again a PI controller. This is again a PI controller, and this gain K1 I told you that because it is scaling from output to this load current, right, because this load current, since this voltage is high, will be smaller than this load current. So, that is why it is a scaling by V0 by V bus, because V0 is lower than V bus voltage. So, it is a feed forward, but it is coming from the second stage. Again for the second stage, it is again a PI controller, where the normalization factor is 1 here. Okay. Now, we can apply this tuning parameter. So, the first stage, the tuning parameter, since it is coming from this load step size, that means if it undergoes a delta load step size, then we can easily apply. But remember, we are talking about the first stage, right. So, if there is a delta I0 load step, here it will be reflected as delta I0 into V0 by V bus. That is why this factor is coming, V0 by V bus is coming, because what was our, for a normal buck converter we know Kp is 2C by L delta I0 into your V in into Vq. So, for the first stage, the input voltage is directly your input voltage, this one, Vq that you have to find out. For the first stage, the output, this intermediate bus capacitor is C1 and intermediate bus inductor, for the first stage inductor is L1. So, it is given, and this delta I0 for the first stage is nothing but that we have discussed is this one, right. So, this is replaced, and what is this? So, Vq1, it relates to the output voltage, it is the bus voltage or V in minus V bus, and this is the same method that we are using, where the D1 is the steady state duty ratio for the first stage and L1 is the inductor. Again we are using this concept. Okay. For the second stage, we can use Kp2, Ki2, that means proportional gain 2, integral gain 2. Kp2 is straightforward, it is C2 L2 delta I0, and here it is the bus voltage is the input for the second stage, right, and what is VQ2? It is Vref or Vbus minus Vref, and Ki2 again it is D2 L2, only it will be updated this value, and the normalization factor is this. And this thing we are going to discuss using simulation, because we have discussed in week 3 about how to control the two stage converter and also CPL. So, in the subsequent lecture we are going to see the tuning of this cascaded converter, large signal based tuning. We will take case study with MATLAB simulation. So, today we just finished all the tuning parameter for this cascaded converter. So, with this I will summarize. We have discussed large signal tuning in fixed frequency current mode control. We have discussed large signal tuning in constant on off time control method. We have discussed large signal tuning in hysteresis control method, and we have also discussed large signal tuning for cascaded DC-DC converter as well as the constant power load. So, all this discussed, that means large signal can be applied, and in fact we can also consider boost converter using cascaded stage. So, I am not going into that, but I think the large signal can be applied for a wide variety of converter topology as well as architecture. So, with this I want to finish it here. Thank you very much.